All right, so I am about to work through the check your understanding questions on 9.4, the intro to significance test for a difference of proportions. I'm going to go ahead and roll that straight into 9.5. So I hope this is helpful for any of those of you who need it. But I am turning off the video. You don't need that. All right. So remember, this is the introduction into a difference in proportions hypothesis testing. This is heavily predicated on you understanding the idea of one proportion hypothesis testing, and there's a whole lot connected to the sampling distributions for a difference in two proportions, confidence intervals, the whole nine. But here we go. According to a recent Gallup poll, people who are college graduates are more likely to report they are satisfied with the way things are going with their personal life than people that are not college graduates. Of the 354 college graduates surveyed, 311 reported being satisfied with their personal lives. For the 384 people that were not college graduates that were surveyed, only 301 reported being satisfied. Is there convincing statistical evidence of a difference in the proportion that are satisfied with their personal lives for all the college graduates and all that are not college graduates? So, first things first, I'm going to call this hypotheses. Okay, so null hypothesis. P1 minus P2 is equal to 0. Remember, that's the equivalence of saying P1 is equal to P2, stating in the beginning that there is no difference in those two proportions, where P1 minus P2 represents the true difference or the difference in the true proportions, I should say. The difference in the true proportions of satisfaction with personal lives for college graduates minus not college grads. All right, so what we want is there convincing statistical evidence of just a difference? So it's not necessarily greater or less. This specifically would be an alternative hypothesis that P1 minus P2 is not equal to 0. Remember, this turns into that two-way test or two-tail test where you have to look at both sides. And you just end up doubling the area for one of the tails to get the two-tail probability. All right, so do the results provide some evidence for the alternative hypothesis? Well, P1 hat college grads minus, or the happiness of college grads in the sample minus the happiness of the college of not college grads in the sample would be 311 out of 354 minus 301 out of 384. And jumping to a fun calculator. Hope I'm remembering this right. Helps when you get a decimal. First off, did I type that in right? Sweet. That is greater than 0. So there is some evidence for the alternative, right? There's some difference. So there's no matter what, some evidence. The p-value for the significance test is 0.004. Interpret the p-value. Remember, this always goes back to the assumption that the null hypothesis was true. So assuming, and I know in class we've been doing a lot of speed work where we just try to say assuming the null is true, but I'm going to use the true context like you should, right? So assuming the difference in the true proportions of satisfaction with personal, which that should have said life up here, with personal life college grads minus not college grads difference is 0. The probability of getting P1 hat minus P2 hat being greater than 0.0947 or more extreme P1 hat minus P2 hat being less than negative 0.0947, right? So it'd have to be the two tails. The probability of getting that or more extreme by chance alone is 0.004. So assuming the null hypothesis was right, that there is no difference between the two, that's a wicked low chance or low probability of happening by chance alone. In fact, that is so low that we don't think our null hypothesis was true. Remember, that's the whole idea. A low p-value is when we reject the null hypothesis. We do not think it could have happened by chance alone. So since the p-value equal to 0.004 is less than alpha equals 0.05, we reject the null hypothesis that P1 minus P2 equals 0. There is convincing evidence that the that P1 minus P2 does not equal 0. So remember, we reject the null hypothesis because that is so unlikely to happen by chance alone that we don't think the original condition was true. There is convincing evidence for the alternative. Really, you should put more context with it, but I didn't put the context because I put so much context into the interpreting. You got to have context in one of those two places. All right, so now we are on to 9.5. This one's going to be a little bit longer in some regards, but I'm going to point out a couple of key details. First things first, recent experiment. This is important. As soon as I'm reading this, I'm thinking about cause and effect, right? So not just making an inference about a population, but cause and effect. So we got to be careful with our language. Notice 180 volunteer children can't make an inference about a population, but they were randomly assigned to receive either a stuffed animal or a blanket to help them sleep better. Of the 100 children who received the stuffed animal, 34% reported better sleep. For the 80 children who received the blanket, 75% reported better sleep. Is there convincing statistical evidence? that the proportion of children with improved sleep with a stuffed animal is less than the proportion for children with a blanket for all children, like the ones in the study. All right, so I'm going to start with my big things first. We know we need to choose a procedure. Well, I'm looking at this and I see um, two proportions going on. And I know that I'm looking for statistical evidence. So the fact that I'm looking for statistical evidence, got two proportions. My procedure is a two sample significance test for a difference in proportions. You can also just call that a two proportion z-test. So there's my procedure. So with that procedure, I'm going to have to do some hypotheses. Null hypothesis. I'm going to use some symbols that make sense in the context of this study. So P sub A for stuffed animal minus P sub B for blanket is equal to 0. We're assuming that there's no difference between the proportion of children who slept better, right? And so alternative, let's look to see what it says. That the children with improved sleep with a stuffed animal is less, right? There is evidence, right? 34% is way less than 75%, but is it statistically significant? So if it is less, then the blankets are doing better. That's a higher proportion. And so when I subtract, I get a negative. So the alternative is that the difference in those true proportions is less than 0. Now, whenever I run a hypothesis test, I have to have a significance level. Remember, as we talked about or introduced today, that is the probability of making a type 1 error. So this time, it's actually a pretty darn low chance of making a type 1 error, but I still need to do one more thing. Like I'm looking at all this, I've got my alpha, I've got my proportions, but what does PA minus PB mean? I've talked it out, but if I'm writing this for the AP exam, I got to make sure my readers know. So I define my parameter. PA minus PB is equal to, or it's the true difference in the proportion of children who sleep and the proportion of children like those in the study who would sleep better with a stuffed animal versus a blanket. One thing I want to emphasize and point out here is you have to be careful that you are not making this sound like an observational study with an inference about a population. We are wanting to make it clear that it's that stuffed animal that is causing the better sleep than the blanket. All right, so I believe that's everything with the choose. Let's see. We've got a procedure, we've got a parameter, we got hypotheses, we've got significance level. You don't have to put the evidence for the alternative that can come into the calculate along with the statistic. That's all I do for my choose. Now, check. This is where I'm going to get a little controversial with a few things, but I think that this can be helpful because I personally am actually going to run my hypothesis test in the calculator at this point usually. Now, I know I've got to check for a few things. First off, I need randomness. Do I have this? Be careful. Notice this is not random selection, but children are randomly assigned to treatments. Got to have good random assignment to treatments for cause and effect. Boom. All right, there's my first randomness or first condition randomness. 10% condition kind of goes out the window when you're dealing with experiments, but let me pause this 1 second and go check something. Okay, I just checked to make sure 10% is not needed. Remember, the whole idea of 10% condition is for when sampling without replacement, no sampling, right? We are randomly assigning, not sampling. So no worries about that. And then I do still need to satisfy the large counts so that my sampling distribution is approximately normal. Now, this is where it's going to get interesting. So remember, for my stuffed animal, NA times PA needs to be greater than or equal to 10. Well, when we were doing confidence intervals, we could just use P hat, right? When we did one sample hypothesis testing, we could just use P because we had a single value for P. But I don't have what the true proportion of children sleeping better with stuffed animals is, or for blankets. I just am looking at the difference, right? So remember, this is where we have to actually find a combined sample proportion. And so you can look at the formula sheet. I actually pulled that up over here, right? So when you're doing the hypothesis test and P1 equaling P2 is assumed, or the difference is 0, you can use this. But if you remember, I mentioned earlier that this is where I actually like to use the test on the calculator first. Ooh, I just realized it might get a little dicey. Hold on 1 second. Let me check something. Oh no, we should be fine. Um, I said that because I'm gonna have to go back and forth a couple times. So menu, statistics, statistical test, two proportion z-test, right? You want to do all that. Remember, we don't put our p's, our proportions in here. We put our successes, but stuffed animal was 34 out of 100, right? 34% of 100. This was 75% of 80, so 60 out of 80. And our alternative, I believe, was that P1 is less than P2. Because if you subtract them, you get less than 0. And remember, right there, 0.522, that is my combined P hat, right? We've got P1 hat, we've got P2 hat. I've already got P hat. Now I've got all the other good stuff in there, so that's good. But there's my combined sample proportion. So it would have been nice if we could do the piece of B and piece of A, but I don't have that. I gotta use combined. But I now have that. So let's go do some calculations. So 100 times 0.52 repeating is equal to 0. Or 52.2 repeating, which is greater than or equal to 10. We have, and then the complement, right, would be 47.7 repeating, which is greater than or equal to 10. This would be 80 times 0.52 repeating. I have no clue what that is. 2. All right, 41.778. So 7 repeating. And so then the complement would just be 38.2 repeating. All right, all greater than or equal to 10. So sampling distribution of stuffed animal proportion minus blanket proportion, approximately normal. All right, now calculate, which is always somewhat of a misnomer. Students get upsetty about it all the time. All I'm really doing is plugging values in and then using the calculator to do everything. So I'm skipping the general step. We need to recognize that it's the statistic minus the parameter. And do notice I put my parameters inside the parentheses because it's a single value grouped together, divided by the standard deviation or the square root, so standard error. And so remember again, ideally we would use, nope, not p hat at all. We would just use PA, but P sub A, but we don't have that. And so instead of being able to use that, we again have to use the combined sample proportion for both in this denominator. I know that again doesn't look exactly like what's on the formula sheet, but this brings the formula sheet and what we have been doing back together more closely. All right, so we already did, I have not done p hat A minus p hat B, but let's look at that again. 0.34 minus 0.75. Oh yeah, we did know that. So 0.34 minus 0.75 minus, now remember the whole idea of a hypothesis test is we assume the null hypothesis is true. So P sub A minus P sub B, we assumed from the beginning was 0, divided by the square root of 0.52 repeating times 0.47 repeating divided by 100 plus 0.52 repeating times 0.47 repeating divided by 80. Whew. All right. But remember, we already did this. We made our lives easy. The probability, and so actually I have that z-score, which I do want to point out, I need us to recognize, like as soon as you see that z-score, negative 5.5, essentially, that probability is basically 0. On the normal distribution, we really only go 3 standard deviations to each side. And so draw your normal distribution. There's your mean of 0. Point of inflection is your first standard deviation, etc. But we need to recognize, man, we're way over here. It's a spec. So the probability that z is less than negative 5.47, and so many students are going to be tempted to write, I think it was 8.4 something. No, way off, 2.23. 2.23, but that's not what it says. It says e negative 8, so divided by 10 to the 8th, which is essentially 0. Okay, and so there's my calculate. Now I got to conclude. I don't have a ton of room down here, so I'm going to focus on the traditional conclusion first and not the interpretation. But since the p-value equals 0 is less than my alpha equal to 0.01, we reject the null hypothesis that P1, nope, P sub A minus P sub B equals 0. I still don't have context in there, so I need to put that in here. There is convincing evidence or statistically convincing evidence, statistically significant evidence, however you want to say it. Convincing evidence, the true difference in proportions of children who will uh see, that's what I was wondering about earlier. I remember there was something odd. We don't want to say would in an experiment because that just means that would imply, I don't agree necessarily, but that would imply is we're only talking about the children who are in the study, not just like those in there and who would experience this later. If you say would, that implies just those in the study. And we want to imply that it's going to cause it for everybody. So um, the true difference in proportion of children who will experience improved, or let's say better, more improved sleep. That's the difference in proportion of children who will experience more improved sleep for those with stuffed animals minus blankets is less than 0. And all that again predicated on the idea that in interpreting that p-value, the probability of getting, assuming the null hypothesis that there is no difference in those true proportions, um, the probability of getting that extreme a test statistic or more extreme is effectively 0, almost 0. And so there is all that I can give you for these check your understanding questions. I hope they were helpful and that you can use these to help you improve your understanding. I hope you have a great rest of your day, evening, morning, whenever you're watching this, and see you in class.